Hey everyone! Today I want to discuss an optical method that allows for measuring very detailed height maps of reflective interfaces, and with it we can measure height variations in the nanometer range. The method is commonly referred to as White Light Interferometry or Coherence Scanning Interferometry. At first glance, the two names seem to contradict each other, as coherence is generally associated with narrowband laser light and not with white light. However, every type of light has a certain degree of coherence. It's just that the degree of coherence is very small in white light. And in white light interferometry, it is this very low degree of coherence that we'll use to our advantage. In the rest of this video, I will refer to the method as Coherence Scanning Interferometry or CSI. Not only does this name sound way cooler, it also describes the method more accurately. The measurements involve scanning a coherence condition across a surface. And you don't need white light to do this, just spectrally broad light. To discover how a coherence scanning interferometer works, we're first going to build one ourselves. Now don't get me wrong, I'm not going to build a high-end instrument for this video, just a simple setup to illustrate the principle. And during the build I'll try to explain the backgrounds in quite a lot of detail. After that we're going to take a look at a commercial instrument that I recently bought. It is almost 29 years old, but in my opinion still quite advanced. And in the last part of the video we're going to take a look at a few examples of measurements using this coherence scanning microscope. Let's build a very simple coherence scanning interferometer to discover the principle. And I'll start by showing you a schematic of the setup. This here is a white light source which emits spatially coherent light, and I'll talk about what this means in a few minutes. This light is sent into a 50% beam splitter where half of the light goes straight on to the sample. And this sample contains some structure at the interface, which is indicated here as a small height difference. Now the other half of the light is reflected towards a flat reference mirror, and both the sample surface as well as the reference mirror reflect light back towards the beam splitter. Here the light from the two reflections is recombined and half of this light ends up on the camera sensor. An important part of the setup is this translation stage, by which we can adjust the length of one of the two arms. Also, because it is vital that the reflected light of both arms reaches the sensor of the camera under the correct angles, both the sample and the reference mirror have tip tilt adjustments. Okay, so this is the schematics of our setup, and as you can see it's not overly complex. Now the idea of the experiment is of course that we are going to measure a height difference in the sample surface. And for this test I chose a sample that contains an area with a well-defined height difference, and this height difference is also very small. A little spoiler here, it's actually smaller than 100 nanometers. If you're into optics, you might have recognized this configuration as a variation on the Michelson interferometer. In a standard Michelson interferometer, both arms contain a flat mirror surface, whereas in this case one of the mirrors is replaced by the sample under test. Also, the lens in front of the camera is not really required in a standard Michelson configuration. However, in this setup, the camera image needs to have its focus set on the sample and the reference surface, otherwise we won't be able to do any valid measurements. These are the parts that I'm going to use for the build: the light source, two adjustable tip tilt mounts, one for holding the sample under test and one for the reference mirror, a beam splitter and an IP camera with a 75mm focal length lens for collecting the images. The lens has a bit of a macro extension, and that is because the sample surface on which we need to focus is at a fairly short distance from the lens. Here you see the parts in the configuration that we've just discussed: the light source, the beam splitter, the sample and the reference mirror, and on the other side the lens and the camera. The reference mirror is placed on the translation stage that can move it to and away from the beam splitter, and because this type of setup is extremely sensitive to tiny displacements, I used optical rails and mounts to keep everything solidly in place. Now before we continue, I need to talk about the light source, because understanding the way it works is actually crucial. As I mentioned earlier, the light from the source is spatially coherent. What this means is that in the direction transversed to light propagation, the phase relationships in the electromagnetic field remain constant over the beam. In other words, this light source creates a flat wavefront. But for most people it's hard to imagine what spatial coherence looks like in a broadband wave emitter. So let me show you this in a simulation. Here is a strongly simplified 2D representation of the field emitted by a broadband wave source, similar to a white LED. In this simulation, the source consists of multiple point-like emitters that are placed in a small volume. Each of these emits at a different frequency within a certain spectral bandwidth. If we now examine the intensity and phase of the waves as a function of distance from this source, we observe that the wave patterns become more spatially coherent with increasing distance. But even all the way here, we see that the waves are far from spatially coherent. So instead of placing the source even further away, what we can do is put it into a confinement with a pinhole in one of the walls. This pinhole allows a small angular fraction of the light to pass, and we can then use a lens to collimate the light from the pinhole and create a light beam that has a completely flat wavefront. Yet this beam still contains a broad range of frequencies, be it along the axis of propagation. This is referred to as temporal incoherence because the phase relationships change constantly as a function of time when we compare them in a particular point or plane. So with this configuration in mind, building a spatially coherent white light source is actually not that difficult. We just need a broadband emitter, such as a white LED, and place a tiny pinhole in front of it. Here the pinhole itself was made from a piece of aluminum foil in which I punched a tiny hole, and this pinhole was then glued in front of the LED. The lens I used is an achromat with a focal length of 90 mm. The emitter was fixed in a tube and the position of the pinhole was placed exactly in the focal plane of the lens, creating a strongly collimated beam. And this source produces spectrally broad light that is spatially coherent. Let's take a look at some of the other parts of the setup. Here is an image of the sample that we're going to test together with the reference surface. They're both glass discs that have a very thin layer of chromium on top. And if we look at the sample, we see that there is a pattern etched in the chromium layer, whereas the reference mirror surface has a uniform coating. The main feature in the sample surface is this square area of about 5 by 5 mm where the chromium was removed. And if we quickly view this pattern in a bit more detail under an optical microscope, we see that there is a line of chromium in the center of the etched area. Also, near the top right corner, there is a pattern containing some very small test features. As you can see, the chromium layer looks a bit dull, brownish, and it's certainly not a very efficient reflector like an aluminum surface. Now, why use these two interfaces for the test? Well, interferometry measurements work best if the two beams that we combine have comparable intensity. And so, because the sample with these nice test patterns was cut out of an old photolithography mask, I had to use a reference surface with a comparable reflectivity. And in both surfaces the chromium has about 25% reflectivity. An additional advantage of using a low reflectivity reference surface is that the sample also contains an air glass interface, which has even lower reflectivity, say around 4%. And for this reason, using a low reflectivity reference is also an advantage. The sample and the reference mirror were taped to adjustable mirror mounts and then aligned such that the reflected beams were projected on the camera sensor. And here you see what that looks like in the image recorded by the camera. In the image we can recognize the beam splitter area, which is about 10 by 10 mm square. It shows the reflected light from the sample and the reference mirror together. And what you see inside this area is the 5 by 5 mm square area etched in the chromium. Here you can just make out the line in the center and a part of the tiny test structures. Now the next step is to create an interference pattern from the two reflections by adjusting the length of the reference path to make it exactly equal to that of the sample path. And this is quite tricky because with white light it requires the two arms to have the same length within just a few microns. To achieve this takes quite a bit of fiddling with the translation stage, but when the distances are about equal, this is what you observe, a fairly linear interference pattern that extends over a certain width. And if we move the position of the reference mirror just slightly, the position of the interference pattern shifts perpendicular to the linear pattern. I try to explain why that is in this schematic. Here I have, for convenience, superimposed the sample and the reference surfaces with respect to the distance to the beam splitter, and you observe that if we shift the distance to the detector of one of the two interfaces, the position of equal path length will also shift. And if we change the angle between the two interfaces, the spacing between the individual fringes will change, since each fringe corresponds to one wavelength of difference in distance. Now, this is a color image of the interference pattern, but color is about the presence of very specific frequencies or wavelengths of light. Here it's actually a bit of a distraction, because we're only interested in the total intensity of the light. So that is why from now on we will only look at monochrome images of the interference, and we will assume that the gray level in these images is a measure for the total light intensity. Here is a screenshot of the interference in monochrome. Now let's take a look at the intensity as a function of the position along this line here. It shows that the intensity gradually goes from having large variations in the center to a uniform and average gray value. Here is a similar image where I decreased the angle between the two interfaces a bit. And you might wonder, why do we see this exactly? Now the easy explanation is to say that it's just two waves going in and out of phase. But how does that work with spectrally broad light? Let's dig a bit deeper here. As we saw in the simulation, broadband radiation can be considered the linear sum of many individual emission frequencies. But the simulation also showed that the frequencies are only apparent in the temporal domain. Now consider a single point in space through which a spectrally broad field propagates. It's tempting to think that all frequencies pass this point as individual discrete waves, but that's actually not true, because at any given moment in time there can only be one single value for the electromagnetic field in this particular point. Of course, that value is rapidly changing in time, and the field passing the point might look something like this. However, I have to remark that for clarity I've just drawn the amplitude of the electric field component. Another simplification here is that the field is presented as linearly polarized, which is generally not the case in white light. Anyway, all simplifications aside, these rapid field changes contain the total frequency distribution that we call the spectral bandwidth of the light. But it's an illusion to think that you could actually measure all frequencies present by monitoring it for a very short time interval. Oh. Sorry about that. Anyway, the longer you monitor a wave, the more you can know about the spectral properties. So in the case of the interferometer, the broadband field leaves the light source as a spatially coherent beam with a flat wavefront. It is then split in the beam splitter, reflected by the mirrors and recombined. And because of variations in path length, we will observe local intensity variations in the field at the detector. Now in the last few minutes I showed you exactly this simplified wave pattern. And at first glance it looks like a single frequency wave with some amplitude modulation on it. But that's actually not the case. This wave was constructed from the linear sum of 7 different waves with wavelengths around some average value. Now what we'll do is split this wave into 2 waves with half the intensity, like what happens in the beam splitter, and then we'll start shifting them in time and see what happens to the total resulting intensity. Here are the 2 half waves, and I will now consider just these 2 segments of equal length in both. And we'll start out with a situation where the 2 fields are perfectly aligned because they have both traveled the same distance. And this means that the 2 waves are exactly in phase everywhere in this segment. And so the sum of the field will have the highest amplitudes because every maximum and minimum of these 2 identical waves matches up exactly. By the way, not only in this segment, but everywhere in the rest of the wave. We can now calculate the wave intensity in this sum, which is proportional to the square of the amplitude. And if we integrate the intensity over this whole interval, we get a certain value. Now it doesn't really matter what that value is, what we'll do is normalize this value and set it to be 1. Okay, now look what happens when we shift the bottom field curve with respect to the top one over a quarter of the average wavelength. We observe that the average amplitude in the sum of the fields has gone down, and the integrated intensity over the interval has dropped by almost a factor of 2 compared to the in-phase situation. And when we shift the two fields over half the average wavelength, we observe that the intensity is only 3% of the initial value. It's not zero though, and that is because the temporal variations in the wave amplitude and phase prevent these waves from cancelling each other out completely. So when shifting further to 3/4 of a wavelength, we see that the integrated intensity is going up again, and at exactly 1 wavelength of phase difference, we find that the relative normalized value is actually quite high again, 0.87. But it did not come back to a value of 1, and that is because even though the maxima and minima in this wave are still largely in phase, they don't match up exactly, again because there are multiple frequencies present in the wave. If we now plot the values we have just measured, we see that they show an harmonic intensity variation, and these are actually part of a trend. As the total phase shift increases, eventually all phase relationships between the two waves are lost, and the intensity will always yield the same uniform value when averaged over some amount of time. And this is the essence of the interference phenomenon that we observe. There is just a short distance around equal path length where broadband radiation can constructively and destructively interfere with itself. On a very fundamental level, this also illustrates why broadband radiation can only do this when originating from the same emission source, because the exact phase relationships need to exist everywhere over the complete wave in time. If we now return to the observed interference pattern and take a detailed look, we see that the fringes are actually shifted between the areas where a chromium layer is present and where there isn't any. And the reason for this displacement is a small height difference between the two areas. We can actually quickly calculate the approximate thickness of the chromium just from this image alone. I've measured the shift in the pattern at the edges to be a quarter of the fringe spacing. Now each fringe spacing represents a difference of 1 wavelength of distance covered between sample and reference beam. And by 1 wavelength I mean the average wavelength of the LED radiation that we've been using. So let's just say for convenience that this is around 500 nanometers. This means that the height difference is a quarter of that, so about 125 nanometers, and that is the shift in the light waves between the two areas. Now to calculate the actual height difference, we need to divide this value by 2 because the light waves travel this height difference twice. And this brings the actual step height to about 63 nanometers. So this quickly gives us an indicative value for the chromium thickness. Now, although we can measure height differences in this manner, this is actually not the way that a real coherence scanning interferometer measures surface height differences. Instead of looking at fringe displacements, what it does is scan the difference in distance with a very high accuracy. If I try to do this here by hand using the micrometer, that doesn't work very well because of the extreme sensitivity. But if you do this scanning in a more controlled way, for example using a piezo actuator, it looks something like this. So how do we measure height differences from these images? Well, the interference pattern is of course scanning over the surface of the detector, and its position is a function of the difference in distance, delta D, between the sample and the reference surface. But in every pixel of the camera we can also observe an intensity variation as a function of distance, so while we are performing the scan, which is displayed in these little graphs that show the pixel intensity as a function of delta D. So by taking a specific feature of this pattern, for example the position of the highest intensity value observed in the pixel, we can relate the value of delta D to the height for every single pixel. So this is the essence of how a coherence scanning interferometer works, by monitoring the intensity in the interference pattern as a function of distance for every single pixel. Here is a schematic of our simplified setup again. Now let's turn it into a real coherence scanning microscope. First, we want to be able to see much smaller details in the surface, so we want to use a microscope objective. However, not in the way shown here, because the optics in the two arms of the interferometer needs to be identical, and this would mean that you'd need two identical microscope objectives, which is not very practical. So instead, what you do in the CSI is lose the second arm and then use this beam splitter only to illuminate the surface and inspect the returning light. And in order to create a coherence condition, we'll add a second beam splitter and a reference mirror on the sample side of the objective. And so by just scanning the distance between the microscope and the sample, we can achieve exactly the same effect, but now at a high magnification. In fact, the whole interferometer is placed completely on the sample side of the objective. This is a so-called Michelson objective, where the beam splitter and the reference mirror have been integrated into the objective. The little pipe sticking out here contains the reference mirror. The beam splitter is located somewhere in this square part, and to use it we only have to adjust the distance from this side of the objective to the sample. Let's now take a look at a commercial coherence scanning microscope. It's a 30 years old Zygo Newview 100. Unfortunately, I cannot tell you a lot about the history of the instrument, but the plan is to use it for photolithography research and educational purposes. Mechanically, it's a fully motorized 5-axis system. It contains a large 4-axis stage for translation and tilt over the X and Y axes. Then there is the 5th axis, which is the translation along the Z axis, so the axis that does the actual scanning perpendicular to the surface. The Z position can be set with different degrees of accuracy. There is the rough height adjustment with this large wheel. Then there is the motorized control that can be adjusted using a remote with different speed settings. And then there is the piezo stage that holds the objective, where we can move the objective over a maximum distance of about 100 microns. And the last one is actually the actuator that does the scanning during the measurements. The light source itself is an ordinary incandescent lamp, which looks as if it contains quite a bit of infrared, which is actually an advantage because the broader the spectrum, the narrower the coherence pattern. Let's remove the cover and take a quick peek inside at the configuration. The light from the lamp is made spatially coherent using the optical assembly contained in this tube here. The spatially coherent light then goes straight through a beam splitter and then into the microscope objective where the interference is generated. It then returns to the beam splitter and is reflected to a camera. And the camera has a zoom lens that allows for setting an additional image magnification. And that's all basically. Now, the most complicated part of this instrument is probably the software, and I'm not going to discuss it here, it's really extensive. Instead, we'll just take a look at how it presents the results and evaluate a few measurements done with this instrument. Here is a measurement done on a flat piece of glass. We'll place this surface at the correct distance and angle and then perform a coherence scan. From the scan, the software then extracts the height data for every pixel, corrects it for a general difference in tilt, and then presents these data in different ways, for example in a contour map. Currently it shows height differences of less than 80 nanometers. Now, to put this into perspective, a human hair is about 40 to 50 micrometers. So the total scale in this graph here is 1/500th of the thickness of human hair. In this contour map, we can measure cross sections using markers, and the line connecting the markers results in this surface profile. The peak to valley error in the graph is 0.01 micron or 10 nanometers, and the RMS and arithmetic roughness are 1 and 2 nanometers respectively. Pretty cool, huh? Now, the software can also present a 3D plot, and in case you're wondering what these ridges are, they are traces of grease from my fingers that were left there by not carefully cleaning the surface, and they show up as these large features because they're literally tens of nanometers thick. So here is the sample that we've just looked at. For the first measurement, we'll use the lowest magnification with the 2.5 times Michelson objective. Unfortunately, even with this magnification, we can only observe a small area of the pattern. We can now do a scan in the Z direction and see the coherence pattern scan smoothly over the surface, and then look at the data generated by the software, showing a very detailed height map of the surface. We can now from these data easily measure the step height of the chromium layer with the software, and if we do that we find a value of 59 nanometers, which agrees quite well with what we expected from the experimental setup. Now, even though the height resolution is quite mind-boggling, the lateral resolution over the surface, so in the X and Y direction, is quite limited due to the low magnification of the objective and the low resolution of the camera. So if we want to take a look at smaller details like those found in these test features in the chromium, we need to use a higher magnification objective. Michelson objectives are only suitable for relatively low magnifications. Because higher magnifications require a higher numerical aperture, there just isn't enough space to place a beam splitter and a reference mirror between the objective and the sample. So that is why higher magnification objectives are constructed differently in a so-called Mireau configuration. Here the beam splitter is a half mirror at the bottom end of the microscope objective. This mirror reflects half of the light back on a small reference mirror surface inside the microscope objective, which then creates the interference. Here you see an actual Mireau objective. If you look through it, you can make out the reference mirror in the center. So let's exchange the Michelson objective for a Mireau version and take a look at the smallest test patterns in the corner and see if we can make out any details. I'm just going to quickly show you the result of the measurement with a height map. The measurement shows a similar chromium layer thickness, in this case 50 to 60 nanometers, but we can now measure these values over lateral distances of only a few microns, which personally I think is also pretty cool. Okay, let's try something else like this concave spherical mirror. Now, because the surface is not flat but contains a significant radius, we have to scan over a somewhat longer distance. And here you see the mirror under the microscope at 2.5 times magnification with a circular interference pattern about halfway up the slope of the curve. If we now start a scan, the objective first moves all the way down and then scans upwards. So we observe the position of the interference pattern gradually moving from the center to the outskirts of the image. And here is the resulting height map. In principle, we could even determine the exact radius of curvature in the mirror from this plot. Unfortunately, I haven't found out how to make the software show me this parameter. The next sample is this piece of polished granite. If you look along the surface, it looks fairly shiny and flat. Now, granite is a mixture of different materials like mica, feldspar and quartz, and the crystals of these materials all polish at somewhat different rates, which causes height differences during polishing. So let's take a look at the structure in this surface at 2.5 times magnification first. Here you see the pattern of the coherence scan, which is far from a linear stripe pattern, and here is the resulting surface map that shows height differences up to several microns. The contour maps show that the surface contains quite a lot of deeper pits, and at higher magnifications of 40 times we can take a more detailed look at the slopes of such a pit. It looks like a huge canyon in this image, however it's only around 2 microns deep and 70 microns wide. I think that these pits arise from the empty volumes or pockets present in the granite material that open up during grinding and polishing. Next up is this piece of glass. In a previous video I have etched channels in the surface. Now it's hard to make out any details with the naked eye, but under a standard microscope they look something like this, where these rougher looking areas are the etched parts of the surface. So let's see if we can establish how deep these channels were etched using the CSI. Here you see what the coherence scan looks like. First we observe the interference scanning over the bottom of the channels, then sometime later we observe them over the rest of the surface, and the separation in time is actually because the channels have steep walls and are multiple microns deep. If you look at the measurement data, they show that these are actually 7.2 microns deep. The last part that I'm going to discuss is this piece of stainless steel vacuum tubing. And you can see that the manufacturing process left shallow grooves on the surface with quite a lot of microstructure. And this is confirmed when we put it under the microscope and do a scan at 20 times magnification. We observe a very regular groove pattern. Now the software can give us all kinds of values for the surface roughness like peak to valley, RMS and arithmetic averaged, which is a pretty cool feature because these are generally specified as surface tolerances for the manufacture of parts. Now I looked at many different surfaces ranging from plastics and glass surfaces, fiber plates, zone plates and even chip patterns. And it's truly amazing what you can discover about these surfaces using coherence scanning interferometry. And you don't even have to physically touch the surface in any way and run the risk of damaging it. All in all, I found white light interferometry one of the most fascinating optical methods that I've used so far. And so here we've come to the end of the video. I hope it gave you some new insights, for example about the properties of white light and how you can use them. And I want to end by expressing my special gratitude to the supporters on Patreon and PayPal for their continuing support.